Math 242, Quest to College, Pre-Calculus. I am Joe Vasta, and today we are covering section 6.2, Properties of Logarithms. Properties of logarithms, we've already had a few. Whenever you take the log of 1, it doesn't matter what the base is, you get 0. You do log base b of b, it's 1. Because b to the 1 power is b and b to the 0 power is 1. Log base b of b to the x is x. B to the x is b to the x. And b raised to the log base b of x is x. Those are some properties that we've seen in 6.1. Now, on the PDFs that I include next to this video on my website, I'll have this sheet right here, which is the properties of logs. Now we're going to introduce you to 3 new properties of logs, and they actually have names. The product rule, the quotient rule, and the power rule. And the product rule says if you take the log of a product, it is the sum of the logs. The quotient rule says if you take the log of a quotient, it is the difference of the logs, with the numerator is the first one and the denominator is the one that has the negative. The power rule, sometimes I call this the jumping rule. You take the log of something to the power jumps in front of the logarithm. Now, I'm planning on proving to you why these are true, but I think the best thing I can do right now is to show you some problems, and then we'll come back and maybe we'll prove 2 of them. Okay? So in your homework, you're going to get problems that say this. Expand the logarithm and simplify. Basically, they do not want any products, quotients, powers, or roots within the argument. And look what we have here. We have a product. So we're going to use the product rule, which is called property 5. So I'll put property 5 here, but really it's more important that you understand that it's called the product rule. The base on the log is 10 because it's not there, so there's your common logarithm. And we're going to write this as log 4.5 plus log 10 to the 80. Okay, once again, those bases on those logs are 10. And really, there's nothing we can do here. This is log base 10 of 4.5. But over here, we have log base 10 of 10 to the 80th. Now, remember this property here, log base b of b to the x is x. Log base 10 of 10 to the 80 is 80. Now, if you forgot that property, you can set this thing equal to like some variable like w. Change to exponential form and solve that type 1 exponential equation like we talked about in 6.1. This is log of 4.5. Even if we consider that on this one, there is no common base between the number 10 and 4.5, or at least that one that we can think of. So we have now finished this problem. This guy right here, going from here to here, I could label that as property 3. Everything is simplified. So that is what you do in your homework. Let's continue and do another one. Okay, expand the logarithm and simplify. We don't want any products, quotients, powers, or roots. And it looks like we have a quotient. So we're going to use the quotient rule, which is property 6. So this is log base 4 of x squared minus 1 minus, so there's the quotient rule there, log base 4 of 8 So let's take a look at this. We'll take a look at this off to the side in a different color. Log base 4 to the 8, of 8. This equals some number. We'll call it, we call it W. I'm going to change this to exponential form. So this is what I was doing in 6.1. 4 raised to the W equals 8. Remember we were talking about this is Superman and this is Clark Kent. Now I have type 1 exponential equation. I'm going to get a common base of 2. And I have a power to a power, multiply. We have 2 to this equals 2 to that. And from the one-to-one property of exponential functions, we can set this equal to that. We have W equals 3/2. So basically, we've just evaluated that. Now, had that said log base 5 of 8, we would have a type 2 exponential equation. We'd have to keep it log base 5 of 8. But because there's a common base between 4 and 8, we were able to make that 3/2. Change back to black. So this is minus 3/2. Now, we might feel tempted to box our answer. However, this right here, even though it's not a product, this x squared minus 1 can be factored. And so, that's what we're going to do. We're going to factor it to a difference of squares. Okay, so this was just from the definition of what a log is. That's how we went from here to here. And circle that in blue. And going from here to here was just factoring. But now we have the log of a product. So we're going to use the product rule, which we said was property 5. And so this is log base 4 x minus 1 plus log base 4 x plus 1, and then we have this minus 3/2. So there's no common base between 4 and this variable, so we have to keep these guys the way they are, but we don't have any products, quotients, powers, or roots within the arguments of these two logs. So that completes problem number 2. So let's go to problem number 3. The instructions are expand the logarithm and simplify. Why don't you pause the video and see if you can do this one on your own. Okay, so we have an ln, which is a log base e. We'll keep that in mind. But we have this square root, which is actually a power. It's the 1/2 power. So it's the log of something to the 1/2 power. So we're going to use the power rule, which we labeled property 7. The 1/2 jumps in front of the log, and now we just have ln of pi over e. So we don't have a power anymore, but we still have a quotient. So I'm going to go ahead and use the quotient rule. The quotient rule says we take the difference of the logs, so we have ln pi minus ln e. Okay, so notice we have ln e has a base of e. So this is log base e of e, and using property 2, where it was log base b of b is 1, or you can just set this equal to w and say e to the w equals e, you end up getting that this thing equals 1. So can we do the same thing here with this logarithm? This is log base e of pi. Well, e and pi do not have a common base that we can find, so we have to keep that one just like this. So I have 1/2 ln pi minus 1. I'm going to write this as 1/2 ln pi minus 1/2. And that is a legitimate answer. So that completes problem number 3. And you might be thinking to yourself, back up here, could we have done something differently and written this as pi to the 1/2, e to the 1/2? Yes, we could have. So let me go ahead and in a blue pen, some of you might want to just skip forward. So this is another way. But as long as I'm using the properties of logs correctly, I should get the same answer. So ln pi to the 1/2 over e to the 1/2. So this is, this happens to be, hold on, I forgot to put, this was the quotient rule, so this was property 6. And then this one from here to here was property 2. Not that we have to label the properties, but in case someone's looking at these notes. So now I'm using quotient rule, which is property 6, ln pi to the 1/2. This is minus ln. So I'm just doing the problem again, because obviously this is so fun. Okay. So now I'm going to go ahead and take this power and jump it in front. This is property 7, the power rule, 1/2 ln pi. I can do the same thing there, minus 1/2 ln e. And then this is just ln e, which is log base e of e, which is a property 2. So this guy right here, ln e is 1. So we end up getting the same answer. And even over here, we could have done one of our popping properties, which I called the pop-in property. This is log base e of e to the 1/2, just becomes 1/2. So that's problem number 3. Let's go ahead and do problem number 4. Problem that has products, quotients, and powers, and roots. And what we want to do is expand the logarithm and simplify. So the big thing that I see is a quotient. So I'm going to use the quotient rule, which is property 6. And this says log base 9 of the top minus log base 9 of the bottom. Okay, we have a square root, and if we remember from the other problem, we can replace that square root with the 1/2 power. Okay, over here we have a product. So by the product rule, we have log. Now I'm going to go ahead and write this incorrectly and see if you can catch what happened. So the product rule says the log of the product is the sum of the logs. Okay, so pause the video and think about where the mistake is. Okay, the mistake happens to be this guy right here equals this guy right here. That's a bright yellow. My eyes are hurting just looking at that. And so since the yellow got replaced with the yellow and there's two terms there, the mistake is there should be parentheses. Okay, so let's go ahead and distribute that negative. Okay, now looks like in our arguments we still have some powers, so we're going to use the power rule, property 7, 1/2 log base 9 of x. So property 7, power rule, sometimes I call it the jumping rule because that guy gets a little jumpy, jumps down there. So we have minus log base 9 of 3. And then same thing over here, the jumpy rule. Look, minus 2 log base 9 of y. So it appears that we are finished expanding the logs. We don't have any products, quotients, powers, or roots. There's no common base between 9 and x, because we don't know what x is, and there's no common base between 9 and y. But is there a common base that we can think of between 9 and 3? And the answer to that question is, yeah, I think the common base is 3. I'm going to circle this in green, and we're going to take it up here. Say log, hopefully this green comes out all right on the camera. This equals w. It's going to be good enough for government work. I'm going to go ahead and change Superman to Clark Kent. 9 to the w equals 3. Common base is 3. 3 squared is 9. 3 to the 1. Power to a power is we multiply. 3 to something equals 3 to something else, so that those two things have to equal. 2w equals 1. W equals 1/2. So we can go ahead and replace the thing that I circled in green with a 1/2. There's a minus in front of there. So this gives me 1/2 log base 9 of x minus the 1/2. 9 to the 1/2 power gives me 3. Square root of 9 is 3, so that checks out. Remember that logarithms are just exponents. Minus 2 log base 9 of y. So now we are finished with this problem. The next two problems we're going to do is we're going to take things that are expanded out and we're going to condense them into a single logarithm. And then after a few problems, we'll go ahead and prove some of the properties. Some of you not too fond of proofs, so you can just skip ahead. And that's an advantage of this whole deal in class. How can you skip ahead if you're just sitting there? But here, you just move the little tab. Write the expression as a single logarithm. So we're done with the first grouping of homework problems. Here's the second grouping of homework problems. We want to put this all into one logarithm. The base on that log, since it's not written, it's a 10. Now you might think to yourself, let's go ahead and do the quotient rule, because look, we have a minus here. Notice the quotient rule, if you're going to go from here back to here, you have to have ones in front of those logs. You know, there has to be a -1 there and a 1 there. Same with the product rule. So what I have here is a 4 and a 3 and a 1/2. And they're in front. Maybe they can get a little jumpy, and we can use property 7 and make them jump up and become powers. So that's what I'm going to use. I'm going to use the power rule. Log base x to the 4th. So this is property 7 minus log, I hope I didn't say log base x to the fourth, log base 10 of x to the fourth minus log y cubed plus log z to the 1/2. So now we could take a look at writing this using the quotient rule. So that would be property 6 log base 10. Okay, so we don't have to say base 10. We could just say log of x to the fourth over y to the third. It's a subtract, so these become a quotient. And of course, this one we didn't do anything with. Log of z to the 1/2. So that was the quotient rule. Now we have the sum of two logs. They have the same bases, so I'm going to use the product rule. This is log. Now I have to multiply these guys together. Now if you forgot how to do that, you could, for psychological purposes, put that over 1, and so this becomes x to the fourth z to the 1/2 over y cubed. And this is an acceptable answer. Now, the math nerds, what are they going to do? They're going to go like this. They're going to say log x to the fourth square root z over y cubed. So that's going to make you more marketable in the dating world. Or maybe not. But anyway, so both are acceptable answers. So that's what you're doing in your homework. Some people actually consider these problems, this problem that I did, kind of easier than some of the ones that we did where we're expanding the log. Let's do a challenging one now. Here's the challenging one. Write the expression as a single logarithm. So we might think to ourselves, we can't do that because this 3 is not a logarithm itself. The 3 is just a number. Let's go ahead and talk about property. Which property should we use? How about property 3? Property 3 says log base b to the x equals x. Now I've been calling this the popping property because that goes pop. That's not the proof of why that's true, but it helps you remember it, and those b's have to be the same. Well, just like this thing goes pop, and it's just x, we never said this, but we can go this way and make the thing go unpop. Okay? And that's what we're going to do here. We're going to make this thing go unpop, and the base that we want for the log, we're not going to write b there, we're going to write 2. So, using the unpopping, or the popping property backwards, we're not doing anything with that term. But here it goes. We're going to make the jump back. So this is log base 2 cubed. So do you see that this thing can pop? We end up with the 3. That's the safer way to use it, more comfortable way. But we went from here to here, which is a little more uncomfortable, but we can do that. Now look at these logs. They have the same base, and we're adding them. So we can do the product rule, where we say this is log base 2 of x times 2 to the third. 2 to the third, we could have just done that right away. That's 8. So let's simplify our argument. Log base 2 of 8x. And that is how you do these properties. Now, this is the part where some of you can just skip forward until you see something that says problem 1, log base 7 of 14. But for those of you who care about, you're like, where do these things come from? Let's go ahead and prove 2 of the properties, and the third one you could probably prove if you really cared. So this is abstract, and you won't have to do this in your homework. I'm going to let x equal log base b of m and y equal log base b of n. Okay, so that's where I'm going to start off with, and I'm going to get everything else from that assumption there. Looking out my window, and my cat has a lizard. I think the lizard's dead. Oh, so many distractions here. Okay, so the life of a cat. He's gonna eat it. Crazy times we live in. Okay, this is Superman. I'm gonna change this to Clark Kent. So this is the definition of a log. The base is b, the exponent is x, and this equals m. Okay, so that's just the definition. And I'm going to do the same thing with this Superman too. Base is b, exponent is y, and this equals n. Okay, so for property 5, it says something about the log of a product. So I'm going to go ahead and prove that this is actually going to give me log base b of m plus log base b of n. The first thing I want to do is I want to replace m with something from above here. So m is actually b to the x. Okay, we made that replacement. What can we replace n with? N can get replaced with b to the y. Now, you guys remember that maybe x to the 7th times x to the 3rd. What does that equal? That equals x to the 10th. You add the exponents if the bases are the same, and that's what we're going to do here. Log base b of b, we add those exponents, x plus y. Now, we go to property 3, where that thing goes, pop, you have x plus y. But what is x? Look above and see what we see. X happens to be log base b of m. Plus y, which is log base b of n. And so we've just proved, property 5, that the log of this product is the sum of the logs. Property number 6, that's the one I'm not going to do. You would go m divided by n. You would write something similar over here. The green thing would be on the bottom of the fraction. Do some properties of exponents, and you can get property 6 if you wanted to. I'm going to go ahead and do property 7 because maybe when you first saw that property, you thought that I was just making it up. I mean, when I first saw it, I thought it was strange. Why would the k, how could it just jump in front? Okay, so now we're going to replace n with b to the y. So this is log base b to the y. So that's the green part. And this is raised to the k power. Okay, so when you have a power to a power, you multiply log base b of b raised to the, better be careful here, y times k. Right here we do the same thing where that thing goes pop, and you have y times k. Well, we look up top and we say, what does y equal? Y equals log base b of n. And then we have k, which is just that there. And so let me put the k out front. So this is k times the log base b of n. So we have just proved this guy right here, that equals that. And look, the k jumped in front. And we also proved property 5 where that equals that. Okay, so this is probably not going to help you. I mean, it might help you because then you can see that these properties didn't just get pulled out of a hat. But you're not going to be doing anything this crazy in your homework. So I think we should go back and finish off what we were doing here. So I'm going to go ahead and ask us to evaluate log base 7 of 14. Okay, so this right here, there is no common base between 7 and 14. We may have put this problem up in 6.1. I don't know if we did, and then we said we cannot do this yet. Now we can. So how are we going to do this problem? Log base 7, 14. Well, you don't know what something equals in math and you put an x, you look 10 times smarter. Sure, you don't know what to do from there, but at least, hey, it looks like we know what we're doing. This guy right here is Superman. Use the definition of logs to change him to Clark Kent. The base is 7, the exponent, x, and the argument is 14. So now here's something that we did not know we can do, and that would be logging, and I'll do the ln, logging both sides of the equation. Now the reason that works is because the log, whatever base it is, but we'll just say the natural log is a one-to-one function. And so with one-to-one functions, this will equal that. We can get a little more theoretical, but I think after those verifications of property 5 and 7, we'll just take it this way. We have log of this equals log of that. The one-to-one property says that this has to equal that. Now, why would I do that? I've just made this problem more complicated, it seems. What I'm going to do is I'm going to take this x, and I'm going to use property 7, the power rule, and jump that x over here. And now, x is what I'm trying to figure out. Now I can see that x is, I'm going to divide both sides of this equation by ln 7. It's just some dumb irrational number. It took offense when I called it dumb, so maybe I shouldn't say some dumb irrational number. And we end up getting that. Now, could we cancel the 14 and the 7? Absolutely not. We don't have any logarithm rules that say you can do that. We can't. Like if this was f of 14 over f of 7. We've never said, hey, this is f of 2. So we can't, you know, we've never gone like this, f of 2. I mean, that's bad. Where's my pen? So we've got to keep it like this. Now here's the deal. When they came out with logarithms in the 1600s, they also had a table of logs, of natural logs, common logs. They had some tables out there. But now the tables are in our calculator. Now I don't know how well you can see the calculator because there's a glare from the light from where I'm sitting. But your calculator has an LN button and an LOG button. So the natural logs and the common logs. So I'm going to go LN 14, that's what I have here, divided by LN 7. I want to see if this is coming out. I don't know if you can see it. That's what it looks like on the calculator. And when I actually hit enter, I get a long decimal. So it looks like this. The calculator says 1.356207187. The calculator probably rounded it, but it keeps going. So when they ask you to evaluate these things, they'll, you know, they should tell you, you know, we want 4 decimal places, maybe 5. Let's do 5. 5 decimal places, which means 1, 2, 3, 4, 5. So that means you go right here and you say, is that going to stay as 0 or round up to a 1? Well, you look to the right of there and there's a 7. So yes, when I go ahead and write out the final answer, this is 1.35621. And so now, so here's your log tables, and in the 1700s, 1800s, they didn't have these. You would look them up on something that looked kind of like a book, you know, or sheets of paper, and you would get this. So now we know that if we had 7 and we took it to this power, it would give us something that was really close to 14. And I say really close because this is an approximation. Okay, so that is how you do these problems. But here's the deal. Remember when I LN'd both sides? I could have LOG'd both sides. If I LOG'd both sides and you follow this through, so we're done with the problem, so I'll use blue ink. So if I used LOG, I would have got log 14 over log 7, which I could have put on the calculator, and I'll put that on the calculator right now. You don't know if I'm faking it or not. Here. Oh, look what I got. I got the same answer. Now, maybe you're going to pick up your calculator and see if I was faking it. Well, I could have used any base. Now, my calculator does not have log base 19, but I could have changed it. I could have log base 19 both sides and carried through, and I would have had log base 19 of 14 over log base 19 of 7. So basically, you might already have your properties of logs sheet out, but we never wrote down, this is our last property, property 8, that says we have a log base b of n, and we don't like that base. See, we didn't like that base, and we wanted to change it to a base that was in our calculator. This equals, well, so you could change it to any base you want. We'll call that base A, and we end up having, look at the 14 was on the top, and the 7 was on the bottom. So the argument's on the top, and the base is on the bottom. That's property 8. And when we did this problem, we kind of reinvented the wheel, that this thing already existed. But if I said, hey, just use property 8, there would have been some of you would say, well, why is that the case? Because it works out each time exactly like this. So what I think we should do is the next problem where we are evaluating a logarithm. So here's log base 12 of 2.5. Is that 2.5? It looks like 2 times 5. It's 2.5, okay? And let me go ahead and reproduce this property 8 here. Log base A of n all over log base A of B. Okay, so this is property 8. Put a box around it like I did over there, and so what I want to do on this is I'm going to do 5 decimal places like I did on the last problem, but now let's, when you do your homework, you don't have to do all that work again. You can use this property, and I'm going to change this base to any base I want. I'm going to use log base E, ln over ln, or I could write log base E, so E is what I'm changing it to. Now here's the deal, we don't want to mix this up. One of these numbers is going to go on the top, and one's going to go on the bottom. The one that goes on the top is the one that's above. That's how I remember this. 2.5 goes there, and the one that goes on the bottom is the one that's lower down, and that happens to be 12. So on my calculator, like you really want to see me press buttons on the calculator, I'm going ln of 2.5 divided by ln of 12, and this gives me 3, so this gives me 0.368742517, and it keeps going. So this is going to be approximately, we're rounding to 5 decimal places, 1, 2, 3, 4, 5. Is that going to stay a 4 or become a 5? Well, there's a 2 there, so it's going to stay a 4. 0.36874. And that's the answer. Which means if I took 12 and raised it to this power, I would get something really close to 2.5. So there's change of base. Do a few more properties here, or problems. Change log base 5 x minus 3 to base 10. So let's use property 8. I want to change it to log base 10. Now I don't have property 8 written here, but let's see if we can remember it. So, changing it to base 10, which one goes on the top? The argument. The one that's above. Which one goes on the bottom? The base. And usually when we write log base 10, we don't write the 10 there, so I'll write out the final answer, log of x minus 3 over log 5. So that's change of base. Let's go ahead and do another problem. We're going to go back to that second grouping of problems in the homework where you may get something like this. Write as a single log. So we've already done some of these, but I saved this one till after we did property 8. The deal is I want to change the base. And I can pick which one. I'll just pick this one. I want to change this because I can't add these because they're different bases. But when they're the same base, I can do the product rule. Notice the product rule. The bases have to be the same, and here the bases are different. So I'm going to change that to base 3. How do I change this to base 3? I go log base 3 on the top, log base 3 on the bottom. Now it seems that we might make a mess here, but let's just go ahead and do this. So the argument goes on the top, argument, and the base becomes the bottom argument. And this guy's just watching the show, and he's like, man, I'm glad that's not happening to me. So that was property 8. Now log base 3 of 9. Hopefully you're already learning how to do these quickly. 3 to what power gives you 9? But if not, you can always set it equal to W and do this. And say, oh, common base is 3, W equals 2. So this guy right here equals 2. So log base 3 of x plus, we could write log base 3 of x plus 1 over 2, or we can write the 1/2 right there. Okay. Now, can I do the product rule? And the answer is no, because of this 1/2. But we're going to make this 1/2 jump and become the power using the power rule. That's property 7. So log base 3 of x plus log base 3 of x plus 1 to the 1/2 power. And now I can use the product rule, where I write this as log base 3 of x times this. This right here is an acceptable answer, or if you want to be a little extra math nerdy, you can, first of all, you've got to breathe a little heavier and get excited with math, and you could put the square root there. So there it is. So both of those answers are acceptable answers, and that happens to be 6.2. So for some of you, you can stop the video. So right here, so now is the time to stop the video if you are doing the bare minimum. Okay, so this is optional. And the optional part is, why are logarithms helpful? Why? I mean, they almost seem pretty stupid. Well, what we're going to do is we're going to talk about astronomers. And astronomers back in the 1600s multiplied really big numbers together. Like if you had to multiply this number, I'm just kind of making this up here, multiply that by 23,456,789. Now think about doing this without a calculator. This, so let me put astronomer here. This would be painful, especially if you had to do a lot of these things. So this is what happened. Napier came along with this definition of logarithms and said, let's call that number m and this number n. And so instead of doing this, because we don't want to do this, we want to go like this. We want to go m times n. That is our goal. But what we can do is take the log of that. Okay, the log of m times n, log base 10, we'll use the product rule. This is log of m plus log of n. And then with these, so this is log base 10 and this one's log base 10, you look these up on the table. So actually I'm gonna, I don't know if I wasn't planning on doing this. So I end up getting, for the first one, this one right here, I used a calculator because that's my table, but they would be using pieces of paper and all that stuff. They'd get something that looked like this. And then we'll look up the other one on the table. So I have 2, 3, 4, 5, 6, 7, 8, 9. And there's an error there. Nice. Okay, So what did I do wrong? 4, 5, 6, 7. Oh, I put 2 parentheses in there. And for this one here, I'm getting 7.3702685561. So I looked those up on the log tables. And what do I have to do with these numbers? They look kind of as long as those numbers. There's decimals there. Instead of multiplying really big numbers together, I could just add them. And without a calculator, I mean, adding is a lot faster than multiplying. So let me go ahead and I'm going to add that to, of course now I'm doing it on the calculator. What's wrong with me? I guess I'm not really a purist when it comes to this. 4968. And so I'm getting, you know, I mean, I didn't want to spend a lot of time adding them. So it looks like this. Wait, must have done something wrong. Oh, maybe. Okay. Well, anyway, so let's just say it's like 16.4. Okay. So that is not really what those guys are. We know that log of mn, you know, is approximately 16.4. I'm still kind of upset with my adding. I don't know what happened. Oh, it must have been, there's something happening in the calculator here, so, you know, please don't tell people. I mean, there was some carrying going on here, but it's about 16.4. So we have that. We can actually change this back from Superman, which has a base 10, to Clark Kent. So this is going to be 10 raised to the 16.4 is approximately m times n, and isn't that my goal? And this would probably explain why sometimes when people are doing astronomy, they have things that are written as 10 to some powers. Besides the fact that illustrates really big numbers, it was sort of motivated by the logarithms. So that is it for 6.2.